In this recording, we're going to look at compound events. Let's start with some definitions. So a single event might be these, for example, a card being drawn, a coin being tossed, a die being rolled, a person being chosen. It gets a little more complicated now when we have compound events. Those are typically like an and and an or situation. 2 cards being drawn, a coin tossed 4 times, 3 coins tossed, 2 dice being rolled, 4 people being chosen, etc. Hopefully this is obvious, but probability with replacement means you're going to replace that object and it can be chosen again. Okay, so if I draw an ace from a deck of cards and then I put it back, it's possible to draw that ace again, and so there's still the same amount of cards. We have some expectations here. We're making some assumption that you know a little bit about cards, and that we should consider real quick. If you're not a person that knows anything about a deck of cards, there's 52 cards total in a deck. Okay, there's 4 suits. All right, there's 2 red cards, which 2 red kinds of suits. Those would be a heart and diamond. And there's 2 black kind of suits. There's the clubs and the spades. Okay. And each suit has 13 cards. Okay, it has doesn't have any ones, but it has 2 through 10, the numbers. Then it has a jack, a queen, a king, and an ace. Okay, so there's all of those for each of those 4 suits. 52 cards total. So, if I have probability without replacement, I will draw that ace and not replace it. So now I'm drawing from 51 cards, right? Because I don't have that card in there. All right, so finally, the counting principle. You've done this before. There's A ways to count one event, like picking toppings for a pizza or something like that. B ways for a second event, like the different drink choices you might have. And so you multiply A times B because it's an and situation. And you can have 3 or more events. So let's dive in and look at some problems. How many outcomes are there when you draw 2 cards from a standard deck without replacement? So the way I like to handle a counting principle is something like this. I'm going to lay out 2 places that I'm going to fill with numbers. So the first event is drawing a single card from a deck. So there's 52 ways that card could come out, right? Without replacing it, meaning I only have 51 cards left. So you just multiply those 2 values and we get 2,652. How many outcomes when you draw 2 cards with replacement? Well, again, you've got your 2 events. It's an and situation. I want this card and this card. So an and we multiply. 52 the first time. You put that card back, you still have 52. So that increases the total, 2,704. Finally, let's make it complicated. Flip a coin, roll a die, and draw a card. So why don't you lay out, how many spaces do you think there are? What amount go in each space, the number of ways for each event to occur, and then do the multiplication. Play the recording when you're ready. Okay, so if we've got something like this, you got 3 spaces, 3 different events. Flip a coin, heads or tails. Roll a die, 6-sided die. Draw a card, 52 kinds. We're going to multiply all of them, and you're going to get 624. Our next scenario is rolling a 6-sided die, so it's a normal number cube, right? And you flip a coin. We're now going to get into some probability. So what's the probability that the die shows a prime number? Those would be numbers like 2, 3, 5, 7, 11. Numbers that don't have any other factors other than 1 in themselves. And the coin lands tails up. So first of all, we're going to include a tree diagram or the sample space to support your answer. So why don't you make a tree diagram for all the possible events that could come out from this experiment. Play the recording when you're ready. Hopefully you took time, you paused and you did that. Okay, so this is called a tree diagram, and we want to identify, okay, how many have the desired outcomes? So we're looking for a prime number first off, so that would be our 2, 3, and 5, and it's tails up. So 2 with the tail, 3 with the tail, 5 with the tail. So I counted 3 over, well, there were 12 possibilities, 3/12 or 1/4. Remember, you don't have to simplify your fraction. You can write it as a percent if you like. There are all lots of ways to represent the answer. Okay. Big idea here. We're going to get more into this in our next lesson, but this notion of independence. So if you're spaced out, concentrate here. Two events are said to be independent if the result of the second event is not affected by the result of the first. So if it's an and, like we've been looking at, like A and B, or roll a die and then flip a coin, the probability is just multiply those two probabilities. So the probability of A and B, assuming these are independent, like the coin didn't care what the die did, right? They have no effect on one another. You're just going to multiply. It's the probability of A times the probability of B occurring. Okay. So we're going to set up a Venn diagram to answers questions 4 and 5. Maybe I can set up the first one to guide you on what this might look like, and you can set up number 5. Okay, so set up a universe like this. The rectangle represents the universe, all the possibilities. And inside we have the two events that we're interested in, an ace or a 4. Okay. So sometimes we list out all the different, the sample space basically, all the different outcomes, we list them here. Sometimes we simply say how many, and this is a case where there's 52 cards. We're not going to list every different kind of card in here. We're just going to say how many. So first off, how many aces do you have? Well, remember there's 4 suits. So you've got 4 possible aces. And then you have 4 different 4 cards from the 4 suits. Well, that leaves 44 cards because there's no cards in common. There's no card that has an ace and a 4 on it, right? So taking those 8 cards out from the 52 that we had, that means there's 44 sitting out here that are neither 4 nor aces. So what's the probability of getting an ace or a 4? Well, you add those. You add the 4 plus the 4. So there's 8. Or 2/13 if you want to simplify it. Okay, again, we took the probability of getting an ace, which is 4 50-seconds, added it to the probability of getting a 4, which is another 4 over 52. We get 8 over 52. Okay, could you work on part 5, please? Play the recording when you're ready. Okay, again, you're going to set up your universe here. Okay, slightly different here. We have to first count all the aces. Well, there's 4, but there's a little overlap because there is one ace that is also a diamond. So there's 3 aces that are not. And of the diamonds, we said there's 13 of each suit. So there's 1 that's an ace and 12 that are not. So altogether, I'm counting 16 cards. 52 minus 16, that means 36 are out here that are neither ace nor diamond. So finally, the probability that a card is an ace or a diamond, well, you count all of them, the ones that are just aces, the ones that are just diamonds, and the overlap, the both. Comes out to be 16 over 52. Or if you want to simplify, it comes out to be 4/13. So again, what did we have to do here? Well, it was the probability of getting an ace was 4 out of 52. Probability of getting a diamond, 13 out of 52. But then we had to subtract that one that was in overlap, right? Whereas up here we didn't have to subtract anything. we just added 4 over 52 plus 4 over 52. There was no common card that was both ace and 4, so we didn't have to subtract any overlap. So in general, our formula for OR would be something like this. Probability of A or B is the probability of A plus the probability of B minus, if there is any overlap, the probability of A and B. Obviously, if there is no overlap, like there wasn't in number 4, then you're just subtracting nothing. Okay, now on to some examples. Number 6 is one I think you can do on your own, so pause the recording, work this one out, and play the recording to see the answer. Okay, so you work this one out on your own. Okay, so this is how we'd set this up. Our evens, well, you've got your 2, 4, 6, but one of them, the 6, is a multiple of 3. Your multiple of 3, you've got 3 and 6. And then out here, you've got the remaining numbers are your neithers. That would be the 1 and the 5. Okay. Next question is pretty challenging. Let's go about this 2 different ways. Okay. First off, I'm going to kind of do it reasoning about it. Then I'm going to show you something called a hypothetical 1000 table. But before I show you that hypothetical 1000 table, let's dive down and have you work on question 8. Okay, this is called a two-way table. It's got male and female across the top, going to college, not going to college. You could think of a male and not male. So it's an either-or situation. Here we have an either-or situation. I know we are much more sensitive now to transgender and everything. Just for the purposes of the problem, let's just assume male or female. Keep it straightforward. Okay? So I think you're able to identify all the values in I through 1 through 7 here. Just looking up at your table, why don't you do so and then play the recording to check your answers. Okay, so hopefully you did so. NM means the number of males. So the total number of males is 30 here. So if that helped, if you're like, oh, I see, pause the recording, work out the rest of them. Okay, females, 22, college, 29, not going to college, 23. Male and college, well, that would be right here, these 16. Female in college, well, that would be right here, these 13. Female or college, well, we got to do all the females, which is your 22, all the college, which is 29, but then take out the ones you've double counted. Those 13 females that are going to college, you've already counted, take them out. So that last thing, excuse me, should be a minus 13. Okay, so that all works out to be 38. Okay. Now that we understand the structure of the two-way table, that will help us in the above problem. Okay. Insurance company typically try to sell different policies. You've got your 56% of the people that like car insurance policies, 48% have home insurance policies, 18 have both. All right. I want to find a probability that he or she has at least one. That means they could have the car or the home, or they have both. But I can't just add up all those, obviously, because that would be more than 100%, right? And that doesn't make sense. So something like this. Basically what it means is we've got probability of car or home. And as we saw before, that can be probability of getting car policy plus the probability of having the home policy minus the probability of car and home. All right, so do we know the car? Yes, 56%, right? And we know the home. Yes, 48%. And we're going to take away the both, 18%. All right, so when you just add those up, that works out to be 86%. Now, the probability that he or she has neither, well, that means the opposite, right? This is, she has at least one. This is, it doesn't have at least one. So that would be something like probability of neither could be found by doing the complement, 1 minus the probability of at least one. So I do 1 minus the 0.86, which comes out to be 14% or 0.14. I want to show you a technique here that I think is really powerful for visualizing it, because some of you are like, oh, I don't know if I'm going to remember that formula. Check this out. I think it's very powerful. We're going to make a table that we call a hypothetical 1000 table. It might sound, whoa, that sounds complicated. So this is like method 1 formula. And up here would be method number 2. We call this a hypothetical 1000 table. Okay. So, can you make yourself a table that is a 4 by 4? Once you've set up your table, we're not going to put anything in the top left corner, but just like we have in the male-female going to college, we've got total on the far right and on the bottom left. Okay, and then we need the two events. So the first event was car policies. You've got car policy, no car policy. Home policy, no home policy. Oops. Alrighty, and now we're just going to put in arbitrarily 1000 here, because we're just going to say, okay, we've got 1,000 people, because what does it matter? It's a percent. We can have hypothetically any amount of people. You could have 47 here if you liked. It just wouldn't be as easy to get percents of it. The number to put here in the bottom right should be a power of 10, like 100 or 1,000. We'll start with 1,000. It's usually fine. What you don't want to have is any decimals in here, because they represent people. So check this out. If I want 56 of all the customers, that means 56% of these 1,000 to have a car policy. That means in the car policy, it's got to be 560, because that would be 560 over 1,000 is 56%. Well, right away I can fill in this number, right? I know what it adds up to horizontally. This plus this equals 1,000, so that's going to be our 440. You following along with that? Does that make sense so far? All right, now 48% have home insurance policies. So think about where we can put something related to that number. Hopefully it occurred to you to put a 480 right here. That's the number out of 1,000 that would make 48%. Then I can fill in this, so that's a 520, because those add up to 1,000. Okay, 18% have both. So think about where that number goes. Hopefully it occurred to you that that would be a 180 right here, car and a home. Well, then just fill in the rest of it. So that's got to be a 300 going across to add up to 480. Coming down, that's got to be a 380. And then going across and down, it's got to be a 140. Okay? So this nifty little table is going to allow us to conceptualize the answers to these problems. So now it says, okay, I want at least one of the policies. So it would mean we'd count all the car plus all the home. But then I'd have to take away the overlap. So the 560 plus 480 minus 180, that's essentially what we're doing right here. 56 plus 48% minus 18%. But I like the visual here. The second question, find the probability that she has neither. See if you can find that in the table. Where's the neither? Hopefully you found it right here. That 140 people out of 1,000 don't have either policy. That's 14%. Thanks for watching.